Thank you for the introduction. As I already mentioned, I have a few affiliations. So first we'll give a little bit some kind of background, what kind of research is actually going on at the University of Bonn before I start actually with my lecture. So at the University of Bonn, we have actually a very nice ecosystem with a focus on AI and robotics. I just want to mention the Lamar Institute for Machine Learning and Artificial Intelligence. So this is one of the 6 national AI competence centers, which has over 40 PIs. We have also recently founded a ELIS unit for North Rhine-Westphalia, which actually covers all AI researchers in all universities in North Rhine-Westphalia. So I'm currently the director, and it also has support for PhD students and also workshops and so on. And the last thing is maybe for people which are more from an industrial background, I also want to emphasize the AI Service Center West AI. This is like there are 4 national AI service centers. The focus is actually the target group, people from small companies, and it provides support for developing AI tools as well also like computational resources. So the focus is here mainly for people from industry, but if you're from research, you can also request some computational resources. I also want to make a focus on the robotics part. So we also have the Center of Robotics. This is actually also part of this Robotics Institute Germany, which is also organizing this kind of the lecture series. And we also have a cluster of excellence called PhenoRob, Robotics and Phenotyping for Sustainable Crop Production. So the focus is here using machine learning, using robotics for crop production, and it combines people from robotics, machine learning, but also people from crop science, agriculture, and so on. And the last thing what I want to mention, we also have 2 master degrees. One is actually very new. It's the degree on artificial intelligence. So this will actually start this winter semester. It's also like research-oriented lectures. You have close contact with leading AI researchers. It covers more all relevant topics in AI, and it can do a specialization in computer vision, robotics, NLP, and other topics. It also covers seminars and lectures on ethics, entrepreneurship. And what's also unique, you have their hands-on AI project where you solve problems from other disciplines. So this can be from agriculture, like in PhenoRob, but can be also other disciplines like physics and so on. And we have a second degree, which is also relatively new, which is mobile robotics. This is like a focus only on robotics. So this is just like to give them an overview what we actually offer at the master and also the research level at the University of Bonn. So let's jump into the topic. I have different aspects what I want to discuss and give a little bit an overview about some recent approaches and what are tools to solve different problems. So the first what I want to focus on is on action recognition and action segmentation. So let me first a little bit explain what action segmentation is. What you see here is like a video sequence of like an assembly task. So this is like a data set called Assembly 101, where people have been recorded. It's like a multi-camera setup, including egocentric camera. So you see these glasses on the head of the person, and then person are actually asked to assembly in this assembly different toys. And what you see at the bottom here, the different color codes is like you see each action has a different color. You see it also the names of the action classes in prediction and correct. So correct is the ground truth, and prediction is the prediction what our model actually generates. So this is an example partly for assembly task where you try to monitor the workflow. It can be also used to train new workers to actually help them to actually solve and address the task in a correct way. And I will now discuss a few approaches how this kind of temporal action segmentation can be addressed. And we see that some of these tools can be then also used if we talk about anticipation. So this is just like showing another example from this data set. So what I mentioned before, it's not only exocentric cameras, but here also have the data from an egocentric camera. So it's a camera head mounted, and then you see it also the step. And the approaches are actually generic, but later we'll a bit talk about how we can actually transfer a learned model from one camera view to another camera view. But I come to it a little bit later. So let's look a little bit what we can actually do. How can we actually solve the problem? If you're looking more for a lightweight tool, one of the most efficient approaches are so-called temporal convolution neural networks. So what they actually do is like, this is a very simple illustration. So let's say we have at the input, we have features, the input features, and then technically at each of the hidden layers, you see that based on the errors, you have a dilation factor. So here at the first layer, you take every second frame. The next layer, in the first layer, every frame, in the second layer, every second frame, then every 1 out of 4 frames, and then 1 of 8 frames. And if you want to know what is the context, what I have for making prediction at this frame, you see it, if you look at the errors, it actually takes nearly the entire blue sequence. So this temporal convolution networks with a dilation factor that give me, with very little parameters, a very large temporal receptive field. And we see a little bit later that having a large context modeling, so covering the entire video sequence, that this is actually very important for getting very accurate results. So in order to make it work for video data, you have to do some kind of changes. So the naive temporal convolution network does not work out of the box. So what you can actually do in principle is like you have the same procedure here. So we have the sequence, which can already take the raw video frames, or you already have extracted some kind of the features. And then you have different steps of layers. And again, what we see is the dilation factor 1, 2, 4, 8, always like increase by a factor of 2. And on the right, you see the typical building blocks. So we have a delayed convolution over time, a nonlinear function, typically a ReLU function, 1 times 1 convolution, and a skip connection. So this is like the building block. So to train the model, relatively straightforward. You can simply have a loss function, which actually looks at each of the frames. So T is the number of frames. And you simply want to actually optimize the loss that at the end of the prediction is as accurate as the ground truth. So that would be like a straightforward approach, but it turns out this is not the optimal way. Because at the end, if you add more and more layers, at some point you will not get an improvement in terms of the accuracy. So we have to do some changes. And one of the changes, what is very helpful, is if you make up a certain amount of layers, a reset. So you have your network with the temporal convolutions, you have the multiple layers, and then technically after first stage, you compute a loss, and now you have a reset. So your dilation factor starts again with 0. So you take every frame, then the next kernel takes every second frame, every 4th frame, every 8th frame, and so on. And in practice, it actually turns out you get a huge boost if you go from 1 to 2 stages. You can still add a few more stages, which improve further the accuracy, but at the end, it always each stage increases also the computational cost. So usually, like starting with 2 stages is actually one of the best trade-off in terms of accuracy and runtime. So there are different flavors which actually have been proposed. Obviously, you can have like a parallel branches directly in the first stage. So what you see here on the right, so we have the standard convolution with the factor of 2 to the power of L. So for each layer, you increase the dilation factor, 1, 2, 4, 8, and so on. And in the left branch here, you do the inverse. So you start with a very large dilation factor, let's say 8, and then you go down to 4, 2, and 1. It's just like the inverse order what you have on the right branch. So this actually helps the network to decide at the beginning, should you start with a small receptive field or a very large temporal receptive field. So there are different flavors how we can actually modify this kind of the architecture. So this shows some kind of other examples. Here's like a data set. You have a top view camera, you're looking on top of it, and you want to actually monitor what is the person. So this is called 50 salads because the person is doing nothing else than preparing different types of salads. So the video, what you see here is playing faster, but you see the difference when you change, there's not a big difference, but some of the errors which have been here or a little bit kind of later are a little bit corrected. So this kind of approach actually works very well if you have kind of the video sequence and you actually want to recognize different kind of activities. And also here the activities also in this case always like interaction with some kind of objects like here peeling cucumber or doing some kind of other stuff. So in the black line always shows this is like your current frame, what you're actually looking at. So this is then the green one is just like the action end. This is just like which not annotated, and always make a picture when you have done with your recipe. So this is kind of an example where you can actually use it. And I just want to give an example of another application, and that's more in the context of robots. So this is kind of a data set, a very simple task as handover task. So the robot has to give the human an object, and in this case, you see a failure. So the robot does not release the object, and the human can actually not grasp it. And in this kind of the data set, which has been collected with two different types of robots, the task is actually to detect if the task or giving the object to the human, if this task was successful or if there was a failure. And if there's a failure, what was the failure? Was it like that the grasp wasn't released? Was it that the human did not pick the object? Or if something was spilled, there's a few types of mistakes. So now the input, besides of the video data, we have also some kind of information for the wrist, like force and torque from the gripper, from the hand of the robot. We know the state, if it's open or closed, that is the kind of part. And we also know the robot action because we have the sensors from the robot. So here, if it's approaching to the human, if it currently transfers the object to the person, or if actually like releases it and removes away or moves the handle away from the human. The human action that are not given, but we also try to estimate it using this kind of the temporal action segmentation, what we actually have seen before. So from the architecture is more or less similar what we have seen before. So it's using a temporal convolution network, but now we feed some features from the RGB frames from the video. We have force and torque from the sensors from the hand. We have information about the state of the gripper, which in this case just binary, open or closed. And we know some information what the robot is actually doing, because the robot is doing the planning. And now technically the main task is actually to figure out, which is here on top, was the task successful? So did I give the object as a robot to the human, and could the human actually pick the object? Or the other way around, the human gives an object to the robot, and if the robot could actually take over the object and maybe carry the object to another place. However, what we actually found is technically if our model already tries to predict in addition, even that's not our primary goal, also the actions what the human is doing, then we also get a better prediction of the failure. So the results on the paper, you always see the corresponding references at the bottom of the slides. But I just want to show a few example results. So this is like some kind of the videos. So what you see at the bottom is like the actions of the person, which is a bit annotated. And here you see the ground truth, if it was successful. And here there's just different variants. So let's focus on the MSTCN-A variant. And this, the I3D, this is technically if you don't do any temporal action segmentation, but you directly try to predict, well, if there was be an error. And this is like an example where it's an error. You have seen that the spoon is actually falling down. Also here, when there is an error, you actually try to predict what type of error it actually was. So this is another example of an error. So the person gives the object to the robot, but the robot does not release it. And then technically the human doesn't release it, and the robot cannot actually grasp the object. So this is kind of an example which also shows, so even if your task is actually just like detecting if there's a failure or not, often if you try to actually get more information out of the video, like figuring out what are the activities of the humans, you also get better results for detecting failures. So the temporal convolution networks, this is like usually the first choice because it's very efficient, very easy to train, and can be also applied partly in a robotics context where you might not have the most amount of computation resources. If your computation resources doesn't matter so much, you can also use a transformer architecture. So I'm pretty sure you all know what a transformer architecture is. But technically what it does is like, so we encode the video, or in this case, the image into patches, and each patches is then represented by a token. And in this case is like the transformer encoder transforms the features. And finally, in this case, it just does a classification of the images. So now we want to use this technique for video understanding and using the same task as before. So we have a very long video sequence. Now we talk about maybe 30 minutes. And now the task is the same. We want to segment each of the frame and understand what action is actually going on. So this is actually the idea. The issue is a little bit, since transformers are very expensive, you cannot really apply them to very long sequences because, as I will explain a little bit later, is technically they are actually quadratic in computation with respect to the number of frames. So the first question is a little bit, how can we use this idea to process very long sequences? And as I've just mentioned, think about 30 minutes of video, recording maybe 30 or 25 frames per second. And now you want to compute like the attention between all of the frames. This is actually super expensive. So this is actually the reason, because technically in the transformer architecture, you have the features for each of the frames. You project them down into the queries, Q and keys, and you compute the attention metrics. And this is actually quadratic with respect to the number of tokens. And that makes the approach very expensive. Again, it's like a long video sequence. You cannot compute this kind of self-attention. It simply neither fits into the memory, nor is computation feasible. So you have to do something else. Before I talk a little bit how you can compute the attention of a long video sequence, we also had the first question like, do we need so much context? Because technically you can also mention if you only look maybe like at 1 minute of the video or less, it's enough to identify all the activities which are going on. But at the end, this is like what we did in this kind of study. So it's like, so we trained a model which actually takes 100% context of the video. And how we do it technically, I will explain it in a few minutes, but let's assume we can compute the attention of the entire video. So taking a context very, very large. And just a little bit, make it a little bit clear, for language models, technically, usually you have the words. So the context is actually much, much smaller compared to the number of video frames what you have in the video. So now what we actually did is we actually constrained the maximum context what the model has access to. So 100% means access to the entire video. In 50%, we limit the context to just like 50% of the video, and 25% means 25% of the video, and 12% means 12% of the video. So now if you compare, on top you see the ground truth label. Each color, so this is the duration of the entire video, each color corresponds to a different class. So if you take like 100% of the video context, it's not perfect. So here is a small error, but more or less most of the actions and also the durations are actually correctly estimated. If we now reduce the context to only 50%, here we see more errors and the results getting worse. We get more errors here and here. The lower we reduce the context, what we can give to the model. So this summary, or this actually shows that it actually is very important to actually model the context. The longer, the better. I mean, in principle, we know this from language models, but it's actually also good to know that this is also very important for action understanding or video understanding, also if we have very long videos. So what I have not yet told you, how can we actually model the context if we have so many frames? And this actually works in the following way. So we have actually two options. If you have a very long sequence, so this actually shows, let's say, a simplification of your entire sequence. So each of the blocks here correspond to a token of a different frame. So if your attention, you cannot compute it over all the frames, it's straightforward. You do local window attention. You split your sequence into smaller windows. So red is one window, purple is one window, yellow is one window, and so on. And you compute a self-attention only of each of the windows, independent, in parallel. You concatenate everything, and then you have computed or updated the features of all your tokens based on the feature only in your local neighborhood. So for this update, it only considers the green tokens, but not the yellow or the blue or any other tokens. The alternative approach would be, well, I want to take the entire sequence, but I reduce the temporal resolution. And that you can actually see here. Again, we have the entire sequence. Again, we have the division of the sequence into smaller temporal windows. But now we actually take from each window always like the first frame, so the first red one, the first purple one, the first yellow one, the first green one, and so on. And the same is like for the second part, but now it's like shifted. So here we take the second red one, the second purple one, the second yellow one, and the second green one. So now we also have reduced the length of the sequence and thus the number of tokens. And then we can also compute the self-attention. And then again, if you put this together, we have to reorder all the tokens that they are in the same order. And we also have computed attention. Both approaches have some disadvantages. The local window on the left, here we compute attention only at the local window, but at a full temporal resolution. So the good part is here, we take the full temporal resolution, which is very important if we have very fine-grained action, but we don't consider the entire context of the video. On the right-hand side, we take the global context because there's actually tokens across the entire sequence, but we don't sample the video sequence. So here we reduce the temporal resolutions. And it turns out both approaches are not really ideal, but technically what I can do, and this works actually very well in practice, you combine them in like a single architecture. And this is actually very straightforward. So you first compute the window attention, and then you compute this kind of the long-term context attention. So this is just like locally, but full temporal resolution. This is globally, but lower temporal resolution. And by just like combining them in the interleaved way, then you get actually very good results. And it's computationally feasible. So this shows some kind of the videos. So now we can compute the context for a entire very long video sequence. Again, on top you have the ground truth action labels per frame. You have the prediction, what you have in the second frame, and then you see it like in this kind of the video where when you reduce the context, the maximum context what it can give to the network, and you see it's like the more reduced, the more errors it actually generates. So here the video just only shows the ground truth label, which is like attaching wheel at the moment. But at the end, you see if you compare the color bars between the sequences, you actually see that if you reduce the context, then the accuracy actually goes down. But if you go for 100% context, like full, then you can actually not perfect results, but already very accurate results. And this data set is actually very difficult because you have very small fine-grained actions. So this is actually an easier data set because at the end, yes, less variation of the action, but still a little bit complex because you need to understand with which object the person is interacting with. And also here we see the same behavior. If we reduce the context, then the prediction accuracy actually goes down. And you see it like the prediction labels are less aligned with the ground truth what we observe in the video. So there is a third approach, which also is more efficient than a transformer architecture. So transformer architecture are usually the most inefficient way to model some kind of temporal modeling. And this is so-called Mamba architectures or state space models. So in principle, you can do it in the same way. So you tokenize your video frames, or in this case, an image. And then it's like, instead of having the self-attention, you feed it into Mamba blocks. And what they actually do is like you have a forward scan, so going over all the sequences of the tokens. So this actually shows that the tokens here from the first frame, blue is for the second frame, and so on. And then you have a backward pass where you also go over the tokens. So you have a forward pass over all tokens and a backward pass. And in this way, you are not quadratic in terms of complexity with respect to the number of tokens, but it's actually linear with respect to the tokens. So it's actually much more efficient. However, there is some kind of a shortcomings of this approach, and that I will a little bit explain next. So it's much more efficient than a transformer architecture, but the Mamba architecture also has some issues. And this is actually what we see a little bit here. Let's have a little bit closer look at the plot on the right-hand side. So what you see is here, even it's just like for image classification, but it would be the same for video data. On the y-axis, this is the accuracy. The higher, the better. At the bottom here, you see the models, the parameters of the models. So if you train, just look at the orange curve. If you train a tiny network, 7 million parameters, this is very tiny, you get accuracy about 77%, which is not great, but it's what you get. If you increase the parameters of your model, just adding more layers, straightforward, you increase the size, 27 million parameters, and your accuracy here goes up over 80%. So what they also did, this is from the original video Mamba, it's a specific architecture, Mamba based. If they now increase the parameters to 76 million parameters, if you compare the accuracy, there's little to no improvement. And this is actually not the ideal case, because technically you would expect, because you know this data set, that people have trained much larger model on this data set than just having 76 million parameters. So there's something wrong here. So to do a fix, they also did a workaround. So what they did is like to train the network with 76 million parameters, they augment the loss by using the smaller network to guide the training. So in short, it's called distillation. You take the output of the small network during training, and you want that the prediction of the middle-sized network is similar to the prediction of the small network. So this, on the one hand, you see the accuracy goes up. This is very positive, but it's not the way how you do it. So distillation is usually done in the way you have a large network and you actually want to distill the knowledge of the large network in a smaller network, because at the end you have a very expensive network, which is very accurate, but now you want to learn a smaller network, which is much more efficient, but you don't want to learn it from scratch. You want to just use and benefit from the already trained large model. In this work, they do it the other way around. You take a small model to regularize the training of the large model, and this is just like a workaround. And if you also increase the parameters now to over 100 million parameters, you see again, even with distillation, there's no improvement. So in other words, if you take like a standard Mamba architecture, it has the advantage. It has lower complexity, it's linear with the tokens, but you cannot scale it up. You cannot train large models, at least not in a naive way, because at the end you see it, the accuracy saturates very quickly. Another issue is also like, which is also related to the scalability issue, is the training stability. So what you see is, again, is like the training loss on the y-axis, and you have the number of training epochs when you train the network. So if you train it, the blue curve, without distillation, you have this kind of the jumps. And usually you can have jumps if you change the learning rate in between, but if you don't change it, you should not have such large jumps. So this is an indicator there's some kind of instability during training when you train the network. And the reason why it also has to use this distillation is like, if you look at the training loss, we don't have these jumps, and also the loss goes down much more quickly. So this actually shows that distillation, the main purpose is just to regularize the training data, but this is not a good choice. If you need to regularize the training of your network, then you have a design problem. And the third aspect is also a little bit here, also related. So here we looked at a different Mamba architecture called Group Mamba. So this is mainly for images, and we have the same behavior. You see it again, the training loss. Here's like, again, the training epochs, and what's plotted here is the mean loss, and the shaded area is the variance of the gradients, or of the training loss. So without distillation, you see that technically the variance is actually very high. If you do this kind of the distillation, also here we have the effect, the curve is lower, the training is more stable, and you actually get better results. But distillation is always just like a workaround, and you don't want to use any distillation. The last aspect, which is also highly relevant for practical applications, is the sensitivity to noise. So what you see here is, again, image classification. And now what you do after you've trained your network, you add noise onto your test images. In this case, you increase the compression factor of your images. if you have a high factor, which means like you compress your images, and then 5 already means here you would have very strong visual artifacts. But you see the accuracy goes down the stronger you compress your image. And what it actually, if you look kind of the part, if you have the transformer architecture, which is the purple curve, and the yellow curve, that's the Mamba architecture. And if you look at the difference, the more we compress the image, the gap between the transformer and the Mamba architecture is actually increasing. So this is actually like shows that there technically is the Mamba architecture is more sensitive to some kind of noise and is actually less robust compared to a transformer architecture. And this is like a picked JPEG compression, just an example. It can be also observed for other kind of noise factors, in partly if the noise is related to high frequencies, what you have in your images. So now is the question we have observed, limitation of the Mamba architecture. So it doesn't really scale. And we have a high variation of the gradients, or better to say of the loss during the training. And it's much more sensitive to noise. So it means it's less robust if you deploy it, for instance, like if you have more noise in our sensor data. So the last thing to a little bit to illustrate the impact of noise is like visualized here. What you see is like you have an image, a standard image, what you have. And now what we did is like we look at the frequency, apply the Fourier transformation. And then what we do is like we only look at high frequency part. And then what we do is like we multiply the amplitude of high frequency components by the factor of 10. In other words, we emphasize high frequencies, and then you see it's also some kind of noise occurring in the image. And the more I emphasize this high frequency, the more noise you get, and the quality of your image obviously actually goes down. So now it's a bit interesting to look what information is taken into account by a transformer architecture. So we can visualize, based on the attention, which information is actually taken into account to classify this image, which is a specific species of bird. And let's see, look what is expected. It looks at the head of the bird and also some parts of the wings. That you would expect from a network. If I want to classify it, I look at the bird that's expected. And also, if we increase the noise, there is some change in the attention maps because everything gets noisier, but the pattern remains the same. So the red region here still remains slightly below the head region. And this is like the behavior of a network as it should be. It's more noisier, it's a little bit harder to recognize, but it does not completely change the behavior. Now let's look at the last row. So this is like a Mamba architecture. And now this is actually have a very different behavior. When we increase the noise, the attention maps, they completely change. If we look at the original image, here it looks at different parts of the bird compared to transformer architecture, which is technically here. But if you have like this noise added here, I mean, you can still recognize that's a bird, but it now looks at very different features. And also here, it now looks at some part in the information which is not really relevant for recognizing the images. So this also shows and supports that the state space models or the Mamba architecture is much more sensitive to noise, and it completely also changed how the information is actually used inside of the network. So having the observation that the Mamba architecture has problems, so now is the question, how can we fix all the things? And it actually turns out you can do a very simple fix. So what we did is like you have a Mamba architecture where you have repeating always like the same Mamba blocks. So now what we did, we take one Mamba block and replace it by a transformer block, just a little bit to see how does it impact all the issues what we have discussed so far. So the first what we can see is like if you replace one Mamba block by a transformer block, we get like the blue curve. Here denoted as stable Mamba. So the first behavior is roughly the same. If you have the tiny network, we get more or less the same accuracy. We get a little bit higher accuracy, but this doesn't matter here. If you have the small model, the same behavior. But now it becomes interesting if you move to the middle size. Now we don't have this kind of the issues that the accuracy saturates, but again, we get a nice gain inaccuracy. And this is actually very good because we don't use any distillation, and we can also easily train a model with more than 100 million parameters. You can still add distillation with the dashed line, which also a little bit improves a little bit the training and the results, but that you don't want to use in practice, because the point is like just adding a single transformer block means you can easily scale up the model, and actually you can also train larger models. If you want, you can now go to the billion scale. And the other is like questions like, well, how does it actually change the robustness of the architecture? So again, it's the same plot as before. Y-axis is the classification accuracy, and the x-axis, that's like how strong we do the JPEG compression for the test images. And now what we had before, we had the gap between the purple curve and the yellow curve. The stronger the compression is, the larger the gap is, which means like the Mamba architecture was more sensitive to the noise in my test data. If we just take the stable member version, which is just like what I see here on the left, here also the robustness is the same as the transformer architecture. And this is actually a very nice fix. Means like when you want to scale up a Mamba architecture and you just add at some point a few transformer blocks, then technically many of the problems are resolved. And nowadays, most of the Mamba approaches are actually hybrid models. So you combine maybe some CNN stuff, convolutions together, or with the Mamba architecture, or Mamba with some kind of attention mechanism. Because to have a better scalability, to have better training stability, and to be more robust to noise that you only observe during inference time. So this brings me also a little bit back. So we have now seen 3 different approaches, how you can do like temporal action segmentation. Either we use temporal convolutions, which is by far the most efficient way to solve this kind of the task. And it's my recommendation to start always with temporal convolution networks as a starting point. We can also have seen that technically it's possible to train transformer architectures for this task, but this becomes much more expensive. And the third version is like one can also use a Mamba architecture, which actually have lower complexity compared to transformers, but they have certain kind of scalability issues, which one needs to address in addition. But the other thing, what I also a little bit mentioned, what I've showed at the beginning, so this data set have different videos. So here's like showing the results. What we've seen already before is like the camera looking at the person that actually does the assembly task. So now if we have then the second version is what we have also seen, you can actually have the same task where we have an egocentric camera. So now the issue is a little bit, if you train a model, you might train the model with multiple camera views, but when you deploy the model, the camera configuration might actually change. And now the question is a little bit, how can I train my model that's actually more robust to changes in the viewpoint? So how can I actually have my approach in a way that it generalized to other camera views? And to make it most extreme is the question, can I train a model on exocentric cameras, what we have seen before, and then apply to egocentric videos like head-mounted cameras, what I see here, does it actually work at all? So to make it a little bit work, we have to do some kind of changes during training. So this is the setup. Here we have multiple camera views, at least 2, but it can also work with just like a single camera view. And that's what we have for training. We have them annotated and train the temporal action segmentation model as before. But now the idea is we want that this model also works on camera views, which the model has not seen during training. So this can be a different camera view, maybe more on the side. Or in the extreme case, we train on cameras looking at a person, and then we want to deploy it in a setup where the camera is head mounted from an egocentric camera view. And now is the question, how can we actually train the model that the representation it learns that is actually more robust to camera changes? And there's actually 2 ways how we can actually do it. So the first approach, what we see here at the top, we assume that we have videos, at least 2 cameras, which are synchronized. And that actually means like I have again, the notation. So each of the blocks, think about this is like each of the frames. two sequences, Q and R, are synchronized. So the different colors correspond to different actions which have been annotated for the training sequence. Then we have our network, our encoder, which can be a transformer or temporal convolution network. And this actually gives us then the representation, which is then used for classification. So we have the representation, then we have the final prediction to get like the class labels or the probabilities of the class labels. And then we have the standard loss based on cross entropy, what I've actually shown before. So now what we want to do, we not only want to learn a representation which tries to recognize the actions for each of the frames, but we want to learn a representation that my representation for frame Q is the same as my representation for frame R. In other words, ZQ and ZR should be similar. And this is actually done by computing the cosine similarity between the two representations. In short, we would like that for each frame, this representation is as similar as possible. In practice, one has like a short projection layer, which is just like a small fully connected layer, which actually additionally projects this kind of representation to another feature part, because here some information which is not visible in the other camera view can be actually discarded. So this is the first approach where we add to the standard loss this kind of cosine similarity loss. The second approach here, we do not assume any synchronized cameras. So we have a video where in the video a certain action is actually a bit annotated. And the idea is technically now we want to learn a representation where for this action and this action also the representation should be the same. So now we have different lengths. We extract the representation per segment. So the segments are annotated and it's the same idea. We have a representation now per segment from one video, another segment for the other video. Both have the same action label alpha. And again, we actually want that during training, the representation of the two segments from different videos is similar. So we can actually take only one of them and also combine them. But let's have a look what actually will happen in terms of accuracy. So if we take the baseline, so this is the results when we take the baseline here, that's the blue one. This means like we train the network with a standard loss and we don't have any loss which actually tries to learn a representation which is view invariant. If we take the first part, which is exactly the action loss, which means like here the orange bar here, we do not assume that the videos are synchronized. This gives improvement, but also if I take the first version where we have the synchronized videos, also here we get an improvement. But if I combine both those terms, I actually get a more improvement. And this is like when we train on exocentric views and we also test on an unseen, a new exocentric view and make it more extreme. We train on the exocentric views and then test on a head-mounted camera, completely change of the perspective. And also here training with the loss improves the baseline here from a small value 6 to 9.7. So the results are still relatively low. This actually shows that learning a few invariant representations is actually still a very open research problem. So let's move on. So far, what I've discussed is like we have videos and we want to analyze what kind of action are happening. And now technically what we want to do is like now we want to go like predicting what is the future. So this is partly relevant when we talk about human-robot collaborations, because the robot needs a little bit to understand what the person actually plans, because otherwise the robot is always too late. And this example here, the robot wants to add a jacket or help the person to add a jacket, because here assume the person is injured. And the thing is like if the robot does not anticipate the motion of the person, he will also break the second arm. And this is what you don't want to have. So that's actually very important. If we talk about human-robot collaboration, it's that they're in a way that they're actually useful and not as they are at the moment, super slow. The robot needs to anticipate the intention, the action, and the motion of the human. And this is now in the second part of this lecture, what I will actually give some kind of overview what it can do. So let's start in a setup where we only want to forecast the human motion. So this is just like a simple example. We look only at a single person. If the color is red and blue, in this case, technically, this is the observation. And when they change the color to green and yellow, this is then the foreground motion. So this is just like to give you the idea, what is the change, the meaning of changing the color of the human skeleton. We can do the same also when we have multiple persons, and then it's also the idea, then the persons are in the context, the motion is not independent of the environment, and here also the yellow color here means this like forecast motion, and we also want to do longer term forecasting, not only 1 second, but at least like few seconds in actually longer sequences, and the motion should be social plausible. So that's the target. So the other thing is like when you want a prediction, you want to have multiple predictions. And the technique to do multiple predictions are diffusion models. So I'm probably sure most of you know what diffusion models are, but in case you're not, just in a nutshell, a diffusion model takes an input signal and you add gradual noise to it until everything is just like Gaussian noise. So that's the forward process. That's the uninteresting part. The interesting part is the inverse process. You start with Gaussian noise, and step by step you denoise the image until you get actually the image. And this kind of diffusion model approach, this is like the standard if you, for instance, like generate videos, and you can also use these models for forecasting. The backward process from noise to image, this is exactly the challenging part, and this can be done in an analytical way, because here actually you need a network, and the key of the approaches is like how you design the network. So if you want to generate, let's say, an image from the noise, you start with a noise, you take the previous estimate, the noisy image, and then your network tries to predict the denoised version step by step, and you run it for multiple steps and until you actually get the denoised version of the image. So that actually means that the diffusion process is a little bit more expensive because you don't make the prediction in a direct way, but you need actually multiple steps to get from a noisy signal to the image. So this is an example where the model is not conditioned, but in the forecasting approach, we have the past skeleton motion, and we actually want to predict the future motion. So in this case, technically means like the motion needs to condition on my past poses, and this can be done in a very simple way. So we now take the sequence, we not only denoise the future poses, but we denoise the entire sequence. So we have here, N is my entire sequence. This is my observed poses that I know. This is here in DRC, the X without a head. And this is my future poses, what I want to estimate. And this is like to make a denoising step. At the beginning, I start here with just poses like Gaussian noise. And step by step, this yellow-green poses will be denoised. In a single step, I denoise the entire sequence, but afterwards, I actually override this part by my ground truth or my observed poses. So this is a way how can I condition my past poses or my diffusion model on my past poses. So to have the forecasting, again, we use the temporal convolution network because it's very lightweight and we actually need to do several steps. So to a little bit more in detail, in a single diffusion step, I have the sequence. So at the moment, I look only at a single person. I have my skeleton motion, which include my observed poses and my still very noisy future poses. That's my input in a single diffusion step. I take my temporal convolution network to encode the current state of the poses by a hidden state. And then I have a decoder which updates the poses for each of the frames. And this gives me then here an update of the estimated poses. And then for the observed poses, I again replace them by the observed poses. And for the future poses, I just take like the updated denoised version of my future poses. But this is just like the encoder for a single person. And now if we have multiple persons and we want to actually model the social context or the context of the other persons, because the behavior is not independent of the other persons in the close proximity, we can now need to integrate the information about the other persons. And this is done in the following way. So each color, blue, green, and red, as you see it here, corresponds to a different person. Green, blue, and red. We have the sequence, including the observed and the future poses for each of the persons, we encode each of the persons, the states independently. And now we use an aggregation function, what is here on the right, to combine the hidden states, so the representation of the poses or the sequence of poses of each of the persons. This is then taken as an additional input to the decoder, and then we decode or update the poses of the sequence, taking also the hidden states of the other persons into account. So in the simplest case, you simply compute the average of all the hidden states, but you could also take a more sophisticated function. So now let's have a little bit look how it actually, what it actually generates. So again, the color coding, this is the input motion. And if we change the color, now it flips this like the forecast motion. So in the middle, you see kind of a transformer architecture which fails. So the motion freezes after some time. While if you have a diffusion model, it's actually nicer. It never suffers that the motion freezes. It continues to forecast motion and it does not really get stuck. And it's like a situation where a person actually talks with the other group. So there's not so much action happening here. So the changes are more subtle. And just a bit to see the difference. So here, if I don't couple the motion, I also generate the motion. So we have sequence 1 and sequence 2, because every time when we sample noise, my diffusion models make different predictions for the same observations. And if you look a little bit closer, at some point, all persons talking at the same time. So this is like the issue what they have in the middle. There's not people stop listening, everyone talks at the same time, and this actually becomes unrealistic if this is all the time. If you look on the right hand, here, it still behaves on a long time that actually one is a little bit talking and the other person are still a little bit listening what the person's actually talking. So it's actually more consistent in the group dynamics if you don't couple the forecast motion of all the persons. So this is other examples of kind of motion. So again, the same color coding, but this is just like not really motions which have high interactions between them. Is technically just like motions of different persons, and each of the motion is just like little correlated. It also works in this kind of the context, but if you look at this motion, these types of motion are actually not very interesting. So see, like this person does something which is not related to the other person, and so on. So to study human motion forecasting in context and more systematic, because there are no great data sets available, we also collected a data set. So you see some examples. So we collected a different kind of scenes at the University of Bonn. We have different kind of cameras. You have camera here in this kind of the 3D scene, which means like we estimate the 2D poses. We do triangulation to get the 3D poses out of it. And this data set, because sometimes we have very strong occlusions. So for instance, like you see it here, all the legs and nothing is really available. And some of the kitchen are very narrow. We have some failures, so we corrected the biggest mistakes. But we also have taken 3D scans. So we have the 3D environment before the recording. So we have the 3D poses, the 3D environment. And we also did some annotation in terms of polygons regarding the objects. So for instance, this white one means like this corresponds here to the whiteboard. Then the red are like seating areas, like here this chair and the sofa, blue is a table, and so on. And the reason why we annotated this kind of a box that we see if you look at the video. So this plays the video. You see the person moving around in the scene. And if you look a little bit closer here, people move objects around. And a 3D scan does not have moving objects. But here, because of this polygon representation, if people move around the chairs, we can also capture this kind of information. So this is kind of the data set as it has been recorded. And this showing just like playing very fast the collected data for a single scene. So you see there are different actions. It's actually not only kitchen, but some outer environment. So it's like in the where you have whiteboards, people sitting around, they go to the kitchen, eat, and so on. So this is just like playing a little bit shorter parts of the sequences. So here you see example, someone's explaining something on the whiteboard. There's a discussion here in the kitchen. Also here they're in the kitchen and doing some kind of whatever, interacting with the other, moving to different kind of the rooms. This kind of example of the sequences what we actually have. So this is two examples of the kitchen, which is here the same. And here's like another example. Also here, other kind of scenes. You see people walk around in the scene. We have the context. People here doing something with a coffee machine, cleaning something up, doing some kind of discussion. And that's the data set what we have. And here with this kind of dotted points, this shows like roughly what is the color, different kind of semantic labels, and what is roughly the environment. So it's not a very detailed mesh, but it gives like a rough idea what is the context of the scene. And this data set can be used to study forecasting, taking into account scene environment, scene context, but also the context of other persons. And what we have also in this data set, because we know also the activities, which also annotated. So if you look now from top onto the kitchen, you can also see like what is the trajectories where the person have been moving in the kitchen, or here when they actually had to clean something at the sink. Is you see it also here, the red circle is just like to illustrate where to look. You see the trajectories where of the persons which actually have the activity, which are actually doing something related to the sink, or if the top, how they're actually walking in the 3D scene. So this data set is actually available. If you want to use it for research, you can actually use it. So anticipation at the motion, this is more the fine-grained, but if you go a little bit for a longer time, you might also want to anticipate the action. So what is the intention? What does the person actually want to do in the future? So now just a bit explain the task. We observe a video. So this is the observation. That's my input. And now I want to predict what will do the person in the future. And we do it to phrase the task in the same way what we did for action segmentation. I'm showing the video, stopping here. I'm showing the video, but that you don't observe. That's just for you. The network has not access. That's the future video. And now what we want to do is exactly here at the bottom. So we want to predict the actions, but the actions that happen in the future and not the action that happened in the past. And not only what action will happen, but also when will the action happening. So that's the task what we want to do. So this shows like an example. So you have some video frames as an input. This is not the ground truth given, but we extract what is the ongoing action, like here adds butter to the pan. The red line here indicates until here we have observed the video, and now the model predicts what are the future actions. So here, this is the predictions, and the top row, this is the ground truth, what really happened in the video. The longer you make the predictions, it's clear there is some uncertainty. You cannot really say, well, exactly what will the person doing next in like a millisecond accuracy, but there might actually multiple plausible futures. And that you can actually do by, again, using a diffusion model and not making one prediction for the same observation, but here, sample 1, 2, 3, 4, you make actually multiple predictions for the same observations. And then you see it's like here, because the person adds butter to the pan, the network probably has seen that there's some eggs around, and then it either forecasts, well, either the person might actually still fry the egg, or it actually might just fry the egg. So it's just like different kind of things that can happen in the future. However, it's not only important to model the uncertainty of the future, because we had the issue if you take the raw videos and only predict the future actions. So sometimes you get predictions which are not really understandable. So we predict some action which is not really related. And it actually turned out that there are some cases where there is some uncertainty regarding what happened so far in the past. So for instance, like here, you have bad light conditions. And then it's like if you ask the network to also predict multiple predictions, what it believes is happening in the so far in my video, you see it here, then it either says, well, the person might actually prepare cereals, or it actually might prepare like a tea, or this spoon powder is related to make like hot chocolate. So there's also some uncertainty in the past. And the thing is like by actually predicting the multiple prediction of the past observation and by the future, we get like a better understandable when we make a prediction of why is actually doing the prediction. And in this case, actually, it makes the prediction that the person prepares tea because there's kind of a misunderstanding or some ambiguity in our observed data. So how do we do it? A little bit more in detail. We have our video frames, which defines our observed frames. And then our future part here, we don't know the future, we just do every zero padding. So for each future frame, we simply start with 0. Since it's a Gauss diffusion model, we also have our Gaussian noise. And now technically we combine this counterpart, again have multiple blocks, and then we predict the frames for each noise, for each the frames of the observed frames and the future frames. So that's the network architecture. And in this case, again, we use the Mamba blocks, which means like we have the forward pass of all the tokens and a backward pass. So this is a little bit the architecture, which means like forward and backward pass, you do it in parallel. You change the order, which is the flipping operation. You first run a convolution, a temporal convolution over it, and the S6 block, this is actually the Mamba block, and then you use it again. So this shows some of the results. So this so far is the observation. So the network makes a mistake. So on the one hand, it actually predicts, it actually might pour some serials. It's just recognizing the pouring motion, but it doesn't recognize what object is handling. So I'm going a little bit back in the video. And when the line here gets red, this is my observation part. Now it's here. And now it actually makes the prediction for the future sequence. And you see it, there has been some uncertainty or some mistake in the past. And therefore, we also get different prediction what will actually happen in the future. So this is like what you can see here, and this is like the frames which actually, or the future actions, which actually are predicted. And this anticipation part of the action, this is partly relevant when you want to have a robot that actually supports the human by whatever, providing tools, providing ingredients, or actually knows what the person actually needs next, and also to be at the right time, at the right location. So let's have a closer look at the Mamba architecture, because so far I just mentioned that this Mamba architecture, instead of having the attention of a transformer block, it has a forward pass and a backward pass. So a state space model is actually a linear model. How does it work? So T is the index of my time sequence. I have as an input my current feature. So I have a token at a frame T, xt, which is represented by a feature. It's multiplied by a matrix P bar, and the layer has also like a hidden state, like in a Kalman filter. And then technically you update first the hidden state, given my previous hidden state, so from the previous frame, and the features what I get from my current frame. And then from my hidden state, I generate the output. So this is a very simple linear model. So this matrix is A bar and B bar. I don't want to go too much in detail. They also have some kind of nonlinear component. So we have an exponential function. This delta is a discretization because we compute a state space over a discrete number of frames. But more important actually here is, if you look just at this kind of the model, it's a linear model. And this is not very helpful. Linear models are more or less useless if you want to analyze anything. The reason why this architecture works very well is that this matrices C, the discretization step delta, and the matrix B, they depend on the input features. And this makes the tool very powerful. A linear model is more or less useless, but if your linear components depend on your data and change all the time, then you get actually a very powerful model. And this is like the Mamba model makes this yellow parts depend on your input features. And this makes the model very strong. But if you look a little bit closer, C depends on X, delta depends on X, B depends on X. But what about A? So A is also a matrix, so it should also depend on X. Now, the interesting part is that A is actually, it's not that easy to make A depend on X, because technically what you need, you take your input features, and then you need to actually predict all the values of the matrix A, and A is a very large matrix. So to make it a little bit more efficient, to make A depend on X, what we did is like a different approach, is instead of learning a single A, we actually learn multiple matrices A, and we have a router which actually, depending on the input, it selects one of the metrics, in this case A1, A2, A3. So what does it mean? I have my input features from my sequence. I have some additional learnable weights, and then it predicts my network the probability that one of my matrices A1, A2, A3 is actually selected. And I simply select one where its probability is highest, and this gives me the matrix A. In other words, I learn now instead of one matrix A per block, I now learn multiple matrices per block. And for the inference time, I always select one of the matrices, and this is simply the matrix which has the highest gamma value. So the inference time doesn't really increase, but I have no more flexibility in my model because I learn now different matrices A. So this approach, however, doesn't work out of the box, because technically, if you just train it, what is happening? So E1 to E5 are my different matrices A, what I learn. And then technically it's like the percentage here is like how often is a specific matrix A selected. So if you look at the matrix, the second expert, it's selected in 50% of the cases, but the matrix 4 is not selected, is less than 5%. And this is a little bit problematic because technically you give the network the option to select multiple matrices A, but in most cases it sticks to one. And I will show a little bit later, if you have such a behavior in a mixture of expert model, you don't get very good results. So what you would like to have is more the orange one, where all of the experts or all of the matrices are actually used in the network. And that means like we need to add an additional loss function, which actually balances the selection of the experts. And this loss function is actually shown here. So what we have is the uniform distribution, which means like the probability that an expert is selected should be, in average, with the same probability. So if we go a little back, so in the iter case, we would like to have, if we have 5 experts, so the probability, what we prefer, have a distribution that the selection is always 20%. So it doesn't have to be exactly 20%, but now we count during training. So this part just means like I count how often is an expert or matrix A selected. So if we go a little back, that's like the percentage what I have here, this orange one. So this is like in 30% of cases selected, this in 23, and so on. And now during training, I use the Kohlberg-Leiber divergence, which just measures what is the divergence between the uniform distribution and the current distribution, how often the different matrices A are selected, and add this as an additional loss term. And this, as we seen before, gives me a more balanced selection of the different expert matrices A. And this also has an impact in accuracy. So let's say here, accuracy, higher is better. If actually we train it just with a single matrix A, that's the number what we do, so just like a number. If we train it without this additional loss, but with multiple experts, we don't get an increase. So from 55 to 55.9, that's not a big increase. That's not substantial. However, if we add this kind of loss here, we get actually a jump and we actually improve it. So in a way, you can have an expert model, which includes a routing inside of your network architecture, which depending on your input video sequence, it selects different matrices A at each layer of the block. So now comes the question, if we look which kind of the matrices have been selected for a given input sequence, what does it actually tell us? Is it just like random? Is it just like a certain information, or does the selection of the matrix A depend on the context which is in the video? To analyze it, we did the following. So we look for each test video, we feed it in the network, and we store at each block which of the matrices A1, A2, A3 has been stored. And we encode this information in a large vector and do this for all the video sequence. So what we then do is like a t-SNE plot, which is like, think about like a variant of PCA. And we actually try to project the selection of the matrices A in a low dimension space, just like a 2-dimensional space. And now what you can see it here, we get some kind of clusters. And the color, what you see here, this is not used for the training. So it's just trained, forecast the future actions. And what you have here, this is not the action, this is just like the high-level activity. So for instance, like there are videos which refer activities related to making pancakes. And the action what we forecast is like adding butter, putting eggs, or adding milk. That's like the action what we forecast. These labels are not part of the training. The network has never seen these labels. But the interesting part here is now, if you look at this distribution, and if you just consider which of the matrices A have been selected, we observe that we get clusters, and these clusters, they're not completely separate the high-level activities, but they're quite connected. So for instance, like if you look at all the sequences, test sequence where a person prepares a salad, they actually select very simple matrices A. If we have like activities related to making sandwiches, most of the videos select similar matrices of A. There's a few outliers, but we get kind of a nice separation, not a perfect separation, based on the selection of the matrices A. And this actually shows that the selection of the matrix A, this depends on the global context of the video sequences. And I now want to come to the last part, and that's controllable video generation. So it's related to forecasting. So what is actually the task? So we are here focused on, in this example, on egocentric videos. So we have a head-mounted cameras. Here you see it's a fisheye camera. And if you do just video generation or video forecasting, you take your past observed videos and then you predict your future frames. That's a standard video generation task. Some context frames and it generates the video. But this is not really useful for robotics application. So we now want to use this kind of video generation in a way that it becomes more relevant for robotics or other applications. So the idea is now the following. I have my context frame, so what I have done in the past. And now, because I have a planner on my robots, it plans what kind of action or motion it will execute in the future. Just think about the case when we had this object handover, failure mistake approach, where a robot hands something to the human or vice versa. The robot actually is planning the motion. And here we don't do it with robots, but with humans, because it's part of the data set. So we have given a video, a few frames, and then we add what is the motion, what the person will do in the future. And now the thing is like we want to generate the perception, what the human will perceive when the human executes this kind of motion. So that's the idea. It's called controllable because now I generate a video which is controlled depending on the motion of the person that the person will do in the future. So this is like what we want to do. So I will first explain how it works and then show some results. So we start with an off-the-shelf diffusion model for generate videos. So you have some kind of context frames, which is the current observed frames. We have a standard vision encoder. Again, it's a diffusion model, so we have Gaussian noise. And then we have a standard. Here you see self-attention. MLP is just like a standard transformer architecture. They have a decoder, and then it generates the future frames. So this is like you can start with any video generation model as a starting point. And now we want to condition this model on future human poses. There's actually two ways how to do it. The first is like we give the future poses. Again, we tokenize it, add some positional encoding. And then technically we simply use a cross attention. That means like the videos that are generated, this kind of the tokens what I compute here, they are conditioned on the poses. So it's like a cross attention. That's one approach. The other approach is I do adaptive normalization. So I take my poses, encode the poses. I also have the information, what is my current diffusion step. And then I estimate some scaling, shifting, and gating parameters, and they actually impact the self-attention, the features used for cross-attention, and the MLP layer. So I do a modulation of my features in the screen block. So a little bit more in detail, it's like I have my pose features here, which is the poses there. And then first I have like a network, GE and GM, and they actually learn embedding. And also have this kind of the vectors M, beta, gamma, and G. This just like the nodes. Beta is actually for the shift, gamma is for the scaling, and G is actually for the gate. So there's then a few more operations, so which actually then estimate my beta, gamma, and gating part. And if I have estimated them, then technically I have my normalization layer. So here you see it. I have my input features, I have layer normalization, and then multiplied. So this is the scaling factor gamma, and add a constant value of beta, which I generate from the pose, which is my shift value. And then finally, they're combined. I take my previous features, which are actually coming from this direction. I add the features. I have my gating, which is a value between 0 and 1. And then the self-attention after normalizing my features. And this index K here is either for my self-attention block, which is here, my cross-attention block, which is here, or my MLP block, which is actually there. So this is the way how it's actually done. So before looking at the results, at the videos, let's look a little bit at results, how the different ways of controlling the video generation, how it impacts the performance in quantitative numbers. So there are different metrics to measure the quality of the generated videos. So here we would like to have a higher value, LPIPs, lower is better, here lower is better, and here again lower is a little bit better. So if we now compare the numbers, if we take the layer normalization, here the numbers are better compared to cross-attention. So this layer normalization gives you a better quality of the videos, but if you combine both techniques, we get the best results. But this measures just like, does your video look realistic? It doesn't measure if the video what you generate that's aligned with the human poses what you provide. This is done by the other metrics. And for instance, what I can do is like, let's say this is your context frames. You mark just like for a subset of the frames, which are the hands. And then you use SAM to do this kind of the video segmentation in the videos. If there are minor mistakes, you can make a correction. That means like you have this segmentation in red for the ground truths. And at the bottom, you have the segmentation of the hands in the predicted videos. So now the metric is very similar. You compute the intersection of a unit per frame between the ground truth future frame and the predicted future frame. And when the hands are always in the same position, then the pose which generated is very good aligned with the original videos. So remember, it's egocentric videos, so also the head is actually moving. So it's very, very difficult to task. And if we now compare the results, so we have seen before that the layer normalization gives a better quality of the videos, but if we look at the cross-attention here, we get a better alignment of the hands in the videos with where the hands actually are in the true sequence. And this last errors, this is just like make a prediction of how accurate or how well is the camera motion or the viewpoint of the head aligned what we actually observe in the video. So again, the layer normalization gives better quality, but actually the hands are less aligned with the control. And therefore, if you combine them, we get the best setup, the best alignment with my control poses, and the best video quality. So let's have a look at some kind of examples. So this, what you see on the top, are generated videos. This is not real videos. So what is actually given, we give a context frame, and we provide the pose what a person is doing. So this is a picking action. So here in the middle, the person picks up the ball, the tennis ball. On the left, you see it also the motion, even there's nothing really to pick it up. So it's just like generated videos. So let's have a look at another example, which we actually have here. One moment. So here's like, again, you see kind of the stretching, the hand moves forward and rotates the knob. So that you actually see here. And now this also again generated videos. And we see also there the interaction with the object, even there's no 3D information on the object, is actually quite realistic. So the only 3D information what we have is just a human pose. So now actually the person what he obviously wanted to do, he actually would to put some of the food from the pan on the plate. And then what we say is like, no, move the pan in front of it and rotate it, because also here we have a rotation motion, if you see it there, and that's the motion that's generated. And the same is also here with the lemetta. Also there's kind of the motion where also like the interaction, holding this kind of the object, again, there's no information of the object, everything is just generated. So Now another application. So now it's set up examples where the context frame is now the same, but now we provide different motion for the same context frame. So in the first case, the person is a little bit walking towards the table. Here the person is a little bit rotating, and here's again the stretching motion what we've seen before. So the next example is a bit more interesting because here we have interaction with an object. So again, different kind of motion for the same context. And you see it also like in the generated motion that the objects, how they move, and this is actually done in a different way. So if you compare this kind of videos, everything is a bit generated and the interaction with the objects are quite of not perfect, but they're actually realistic without any 3D information, any kind of information what objects actually are. And this is actually very nice because now you can either use this tool to generate more training data. So for instance, if you want to train a model for estimating poses from egocentric view, or if you want to do some other kind of training data, you can generate more variation of human poses and then generate more realistic looking videos. Or you can use it in a planning approach where you have your model, you do a planning, what is the action, and then the system actually generates what would you actually observe, and you can also use it if maybe your planning will lead to a mistake. So we can also do it with higher resolution. So this is the part technically a bit here. So you see it also kind of on the left, this is actually the ground truth video, and on the right, this is always like the generated video. So again, there, if you look closely, there are some kind of artifacts, but overall, the quality is actually highly accurate. Very good. So just like another example, and you see it at some point, there are still some kind of artifacts, but overall, if you think about the robotics application, the quality is by far good enough. So this is like for longer sequences, so we can also do it for 8 sequences. So see, you see a limitation, because if you look like at the water, and maybe go a little bit back, if you look at the water, it's not really realistic. So the water is not really flowing in a pen very well. But nevertheless, here you can also do this kind of the video generation for longer sequence. And here's just like a person a bit walking around in a bathroom, and you can also do it for longer sequences. So I just like I think we are more or less at the end of the time. I want to just like briefly mention also regarding the video language models. And for the video language model, so one of the tasks is, for instance, like video question answering, which means like as an example, you get a video as your input, you get a question as your input, and then your video language model needs to actually give an answer. So this is just from a data set. So if you really would ask this question, it's a bit questionable, but at the end, this is just like an example of the task that's actually what is actually going for. The issue is a little bit when you add other modalities to language models, this is like a big question. So the language model, what they have, they're actually very good, they're actually very strong, but adding modalities to the model is still kind of a little bit an open research question. And the thing is like there are different ways, and we had a bit of question, how can we add an additional modality without making the model not too expensive? And the idea is a little bit what you see here is you want to have a high accuracy, but you don't want to have too many parameters. And this is, be careful, that's a log scale. So we want to have like a model adding a vision part, but don't increase the parameters of the model not too much. And the size, technically what you see of the circle, this is like the amount of training data what you need for instruction training. So this is a little bit of task. So if you add to an existing language model an additional modality like images or videos, there are different approaches. So in most cases, people start, you have a pre-trained image encoder, you have a pre-trained language model, and then you add some blocks to map the tokens of your vision encoder to the context tokens of your language model. However, that means like you first train the vision encoder and the language model independently. And now in this kind of case, what we do, we directly align the information from the videos directly to the context tokens without the need of having a pre-trained vision encoder. So this makes things actually more efficient. So just like how you train it, just giving the overview. So we have like, we use 350,000 video text pairs, keeping the language model at the beginning fixed. Then we train it on 700,000 videos, where we also now fine tune all the weights of the language model. And then finally, we do the instruction tuning, because this is just like learning and embedding for video and text. And instruction tuning, that's what they do for the task. In this case, a video question answering. And this actually bit shows when you compare to other approaches, when you get actually lower parameters, but the most important is like it also reduces the inference time. And this actually matters because this is the additional inference time what you need to answer a question related to a video versus a question to a text. So if you're adding a video to your question, here it increases only 40 milliseconds, which is very low. And partly if you have let's say a human robot interaction session, you don't want to wait for a long time for the answer. So I think the time is, we are already at the end. I just want to show a few results. So again, this is just like from a benchmark. And this is just like examples from a video question answering. This, like some of the examples, also some of the questions are also related to counting. So some of the questions are actually very simple, but some of the questions are also like related to accounting, and also there, as an example, like this accounting example where, for instance, like vision language model actually are quite good. So this is like an accounting example. So this brings me to the end, and I know if there's any questions, feel free. So thank you for your attention.